Hello all, and welcome to this video where we look at measures of spread of continuous random variables and their distribution functions. As a reminder, the variance of a distribution function is defined as the expected value of x minus the mean all squared. Okay, so we've looked at that in class before, why we're subtracting the expected value. We're effectively finding the difference of the value from the average. Then we're squaring it to remove negatives and positives. And before in discrete ones, we would have to sum all of those up. But that's all taken care of through the integration in a continuous distribution function. So if we look at this and recognize what we looked at in exercise 15b, where we found expected values of functions and then transforms functions, all we had to do as a quick refresher, expected value of x is equal to the integral of x times by f of x, where f of x is the continuous distribution function. Whenever we changed e of x to be some composite function, we're just doing g of x times by f of x. So we can apply that here, where this function inside the expected value, we just put in front of f of x, and we can do that integration. Now, to do that integration, we would have to first find the mean, which is the expected value first. So we're doing one set of integrations for that, get that, which will be a number. It could be, say, 15. Okay, we'll put that in there, and then we'd have to run this integration. Now, that clearly means we've got an x minus a number squared. That in itself is quadratic, times by some other function. So we're going to end up with either quadratic times by some other type of function, or if we're times by multiplying by polynomials, we're going to end up with cubics, quartics, and if not anything larger. But that's what it is. It takes a little bit of work, a little bit of integration work. As always, though, just like any of the other distribution functions, the relationship between variance and standard deviation is the same. The variance is just the square of standard deviation. So if we find variance first, we just square root that and get our standard deviation. As a reminder, though, this formula here for variance is the general formula for variance. We can take a bit of a shortcut, as shown by this formula, and this formula is also, I think it is this version, is on the formula sheet, okay, where it's the expected value of just x squared instead of x squared minus the mean, and then this mean, we can, once we find it, we just square it once. Makes life a little easier. More so for discrete. The difference between doing this and this over here, for a continuous distribution function, the shortcut isn't as significant, but it still helps. So we're going to jump straight into example and have a go. So first off, to think of, this is going to build to finding the variance. Okay, so as we just looked at, variance is equal to the expected value of x squared, take away the mean squared. So the first thing is we have to find the mean. We have to find the mean, then we can square it, and then we can do the rest. So let's do that. Let's find the expected value, or the mean. So expected value of x is equal to the integral from negative infinity to positive infinity of x times by f of x, which is going to be, in our case, outside of 0 and 1, the distribution function is 0, so we can ignore those. So we just work with our domain that's important, which is 0 to 1. We get 3 on 13 x squared plus 4, and I've forgotten the x at the front of it. We need x times by 3 on 13 x squared plus 4, all in brackets, dx. Let's expand this so we can apply our power rule to integrate. So we're going to end up with 3 on 13 x cubed plus 3 on 13, oh, that's times by 4, so that's going to be 12x dx. So we're going to add 1 to the power, divide by the power, so we're going to get 3 on 13 x to the 4, divide by the 4, plus 12 on 13x, add 1 to the power, divide by the new power, so times by 2, all from 1 to 0. That is going to give us 3 on 13 times 4, 40, 52, plus 12 on, so I'm just substituting the 1 here, 12 on 26, all take away, and when we substitute the 0, all of that's going to turn into 0. So we got, what's that, 3 on 52 plus 12 on 26. That is going to be the same as, let's get common denominators, so 3 on 52 plus, let's double that, that's going to be 24 on 52 is 27 on 52. Now, not the nicest of numbers. Can we simplify that at all? Let's check on our CAS just quickly for the sake of brevity. 27 divided by 52, standard mode. No, that's as simple as the fraction can be. So that's our expected value. For whatever this distribution is representing, whatever scenario, that is our expected value. Okay, now we want to find the expected value of x squared. We just found u, we would have to then square it later on, but now this second part, part B, we're going to be dealing with this bit. Okay, so the expected value of x squared is equal to the integral between negative infinity to infinity of, in this case, that's what we're putting in, so x squared times by 3 on 13 x squared plus 4 dx. Again, we're in the range 0 to 1, so we get 0 to 1. Again, expand this, it's going to be 3x to the 4 on 13 plus 4x squared on, no, that's 12x squared, on 13 dx, which is going to be equal to 3x to the 5 on 5 by 13 plus 12x to the 3 on 3 by 13 between 0 and 1 is going to give us 3 on 5 times 13, 15, 8 on 5, 65 on 65, plus 12 on 3, 13, 39, of course. That's subbing the 1, subbing the 0, well, that's going to be 0. Okay, so 3 on 65 plus 12 on 39. Okay. What are we going to... see, common denominators. Okay, I'm going to go about this a random way. I'm going to first divide this by 3, so it goes back down to 13 on 13, and then I'm going to times it by 5, so it goes up to the 65. And I realize I can do that because I'm looking over here that they both had 13 in the denominator. The other thing, actually, I've just realized I could have done, I could have brought that 3 over 13 out the front at the very start in both this step and this other problem before. But this is the way I've gone. So this is going to turn into 3 on 65 plus 12 divided by 3 is 4 times by 5. So it's going to turn into 20 on 65. So that's going to be 23 on 65. And 23 is prime number if I remember right. So that's certainly not going to be able to simplify it any further. So what have we done so far in this problem? We have found, because remember we're working towards finding the variance, which was e of x squared. take away the expected value squared. So we've just found that. That was part B. We found U in part A. Now we're going to combine it. So find the variance. So variance, which is standard deviation squared, is just going to be equal to, as I was just saying, e to the x squared take away the expected value squared is, we just found that to be 23 on 65. 23 on 65 take away 27 on 52 all squared. 27 on 52 all squared. Oh dear. For sake of time and brevity in this video, let's just do that in our calculator, shall we? So that is going to be 23 on 65, take away 27 on 52 on 52. That all needs to be squared. Actually, let's put that in brackets to note. Just to make sure we're in standard, let's execute. Yes, so that's not nice. That's 1139 on 13520. Okay. So that's our variance. So our standard deviation is going to, of course, be equal to the square root of the variance. So that is equal to the square root of 1134 on 13520, which that somewhat simplifies. 5695 on 260, and let's make sure our vincula goes all the way across to make sure that our 260 is not inside the square root. So there we go. That's the main measure of spread that we've talked about, variance and standard deviation. We could find out what that is as a decimal. So 0.29. So in our case, between this 0 and 1, we've found the expected value. So the expected value was, in this first bit, 27 on 52. Which one is 27 on 52? Okay, so to sum up this problem, our mean is approximately 0.519 and our standard deviation is 0.29. So that tells us about our continuous distribution function for whatever this situation may be that is best estimated by that equation. Now that we've gotten those values, we could then do our standard interpretations using, are we not remembering, 66.7% is within plus or minus 1 standard deviation, 95% is within 2 standard deviations, and 95.7 is within plus or minus 3 standard deviations. So we can work from that to then make some interpretations of the situation. So really quickly, a wasp lifespan can vary depending on its role within a quality. The worker wasps have a mean lifespan of 17 days. Okay, so the expected value is 17. Okay, and the variance, which is standard deviation, actually let's write var for variance, is 4 days. Find the approximate interval for the time period in which 95% of the working wasps will be expected to live. Okay, well, period. First we need to find our standard deviation, which is the square root of the variance. So square root of 4 is just 2, nice and easy. So that's 1 standard deviation. So 95%, as it says up here, is plus or minus 2 standard deviations. So the min is going to be equal to mean take away 2 standard deviations, and the max is going to be equal to the mean plus 2 standard deviations for 95% percentile. Sorry, yes, not 95% percentile. This is 95% of the population. So we get 17 take away 4. We get 17 plus 4. 2 times 2. So we get 21, no, not 21. We get 13 and we get 21 days. So we would expect, again, worded question, we now will write a worded answer. We would expect 95% of the worker was to live between 13 and 21 days. The only other measure of spread is the interquartile range. So the interquartile range is a different form of measure of spread, and it doesn't use standard deviations or variance. It's just between the 25th percentile and the 75th percentile. So this is tying back into the previous exercise where we find percentiles. So again, as a graph, what we first look at is we need to solve, if we're given some function, that's our population, okay, our distribution. First off, we find what point A is, so that percentile there makes up 75%, or the area is equal to 0.75. And then we also do it again. We find what this value is B, okay. So that area in there is 25%, or 0.25. And once we have those A and B values, that is what's called our first quartile and our third quartile. And then we can, using those numbers, okay, we would do A take away B. That tells us what's called the interquartile range, which is just the distance between A and B, or the difference of them. So in our previous example, we may have, I'm not saying this is the numbers, but this may have turned out to be that number there is 20, A is 20, and B, not 20, because 20, let's say 20. A is 20, and this might have been 18, not 18, the expected value was 17, wasn't it? So let's say 15, okay. Turns out that less than 75% is 20, less than 25% is less than 15, so the interquartile range will be 20 take away 15 is equal to 5. This can pop up on the exam. It's pretty rare, but standard deviations and variance are a lot more often, and they're just more useful realistically. It's a better measure of spread, because it's more commonly used in sciences and mathematics. But I'll leave it there. You can have a go at this problem if you want to, but we'll leave the video there. That's a quick look at the measures of spread for a continuous distribution function. It follows on again with like most of the discrete stuff, but instead of having to do lots of calculations by hand, we're just using integration. Have any questions, ask in class, or put a comment below. Thanks, and see you.